Hi all of you, I'm Naresh, taking up stoichiometry. I'm from Sri Chaitanya. So we'll try to learn stoichiometry in three simple parts. I'll make it into mole concept, oxidation states, and chemical equations and calculations. We'll try to solve a few questions on each one of them and try to actually make the thing simple. For which, first, we wanted to know what exactly is a mole. So, 1 mole is always equal to gram molecular weight of a substance. 1 mole therefore contains 6.023 into 10 to the power 23 molecules. You know 1 gram molecular weight always contains atomicity into Avogadro's number of atoms. Atomicity into gram atomic weight, which is also equal to 22.4 liters at STP for gases. I wanted to clarify certain important aspects. You can see very clearly. These are the important formulae that you have to learn actually to make the things more comfortable to you. If this is known to you, you can do anything. Now we will see the next part. Now I wanted to clarify what is molar mass. Molar mass is mass of 1 mole of substance expressed in grams. Means sodium 23 grams per mole. Oxygen 16 grams per mole, wrong. 32 grams per mole, correct. Molar mass is always related to molecular weight. Since sodium is monoatomic species, its atomic mass actually is considered. But for oxygen, atomic weight is 16, molecular weight is 32. So once you say molar mass, don't take 16, take 32. Similarly, white phosphorus exists as P4. Therefore, 124 grams per mole is correct. 31 grams per mole, wrong. Hope you understood the concept of molar mass. Then, the next question. I'll take a few things. 5.3 grams of Na2CO3. I am writing two questions. How many, why should I write how many and so on? I'll directly put. It will contain 106 grams contain Na molecules, 5.3 grams contain how many? This is about molecules. Then 106 grams of it contain 2 sodium atoms, 1 carbon atom, 3 oxygen atoms. 6 Na atoms, 5.3 grams contain how many? You know, Na2CO3 produces 2 sodium ions and 1 carbonate ion. Therefore, 106 grams contain 3 Na ions. 3 Na ions, 5.3 grams contain how many? You can very clearly see I have created 3 questions based on this. What is the molar mass of Na2CO3? 106. 106 grams contain Avogadro's number of molecules. 5.3 contains how many molecules? Question number 1. Second question. What is the atomicity of sodium carbonate? 6, 2 sodiums, 1 carbon, 3. So 106 grams contain 6 Na atoms, 5.3 grams contain how much? The same question is asked in ions, then no problem. 106 grams contain 3 Na ions, 5.3 grams contain how many? These are the 3 questions that you can actually get this way. Another one, suppose if anybody is giving you 2.8 grams of C2H4. C2H4, I am writing in a proper way. (28 grams contain), I'll write each one of them, Na molecules, because the molar mass is that. Is that okay? Second thing, 6 Na atoms. Is that okay? Because atomicity is 6 is equal to 6 gram atoms on total, because 6 gram atoms are there. Is that okay? How many carbons are there? 2. 2 gram atoms of carbon. Is that okay? 2 Na atoms of carbon. Is that okay? 4 gram atoms of hydrogen. Is that okay? 4 Na atoms of hydrogen. Is that fine? These are all in 28. And also will be 22.4 liters at STP. If you know all these things, can't you calculate for 2.8? 28 grams contain Na molecules, which is nothing but 6 Na atoms. Total gram atoms are 6. There are 2 gram atoms of carbon. That is 2 into Avogadro's number of atoms of carbon. 6 gram atoms of hydrogen. That is 4 into Na atoms of hydrogen. And the 28 grams being a gas occupies 22.4 liters at STP. From which, if you know 28, you can calculate it for 2.8. This is one type of a question. Then you can also have, suppose anybody is asking, 1.8 grams of water, number of electrons, protons, neutrons. First try to know how many each one molecule of water. Two hydrogen atoms, one oxygen atom, one proton, one electron, one proton, one electron, one oxygen, 8 protons, 8 electrons, 8 neutrons. Thus, a total of 10 electrons, 10 protons, 8 neutrons are there per molecule. 2 protons, 8, 10, 2 electrons, 8, 10, 8 neutrons. Now, these are the number of 10 electrons are there in one molecule of water, 10 protons are there in one molecule of water, only 8 neutrons because hydrogen does not contain neutrons. Now, what will you do? 18 grams contain 10 Na electrons, 10 Na protons, 8 Na neutrons. Then how much will 1.8 contain? This is another type of a question. If you are asked how many fundamental particles, add all of them. This is another one. One more tricky question. Number of molecules present in 18 ml of water at STP. Many people do 22,400 Na, 18, how much? Wrong. Reason, water is a liquid. You cannot apply 22,400 cc concept here. Then how to do density? For water, you know density is equal to 1 gram per cc. Therefore, 18 ml is equal to 18 grams. So 18 ml or 18 grams contain Na molecules. So the number of molecules in 18 ml of water will be equivalent to Na molecule. This is another important type of a problem. Next, suppose if anybody is asking you one atom of an element weighs 6.666 into 10 to the power minus 23 grams. Its gram atomic weight is how much? Simple. Gram atomic weight contains 6 into 10 to the power 23 atoms. Weight of 6 into 10 to the power 23 atoms is equal to 6 into 10 power 23 into 6.666 into 10 to the power minus 23, which will be equivalent, approximately equal to 40 grams. 40 grams will be the gram atomic weight of that particular element. Did you understand? One atom of an element is weighing this much. What is its gram atomic weight? Gram atomic weight is nothing but the weight of how many atoms? Avogadro's number of atoms. So gram atomic weight is the weight of Avogadro's number of atoms. I multiplied the atomic weight of one atom with Avogadro's number and I got 40 grams. This is another one. Suppose someone is giving you 1 gram each of hydrogen, sodium, oxygen, nitrogen. Atoms present in them. Let us say 1 gram Na, because its atomic weight is 1. Sodium 23 grams Na. 1 gram, how much? Na by 23. Oxygen 16 grams Na. 1 gram, how much? Na by 16. 14 grams Na. 1 gram, how much? Na by 14. So this is another one where you can see very clearly, if I take 1 gram each of hydrogen, sodium, oxygen and nitrogen, I selected their atomic weight. You can very clearly see here oxygen I did not take 32, here nitrogen also I did not take 28, I took 16 and 14 and I calculated. These are the number of atoms. If you are asked to write increasing order or decreasing order, it is not an issue at all. One more point I wanted to say is that now weight of 1 mole of hydrogen is one question. Weight of 1 mole of hydrogen atoms is another question. First question, second question. Here answer is 2 grams. Here answer is 1 gram. The reason, this is the weight of 1 mole of hydrogen. 1 mole always equivalent to gram molecular weight. Weight of 1 mole of hydrogen atom, you should not take hydrogen molecule. 1 mole of hydrogen atoms is telling. So you should always take gram atomic weight. So you must be careful about the second question. Here you should not write 2 grams. Did you understand, all of you? These are the various type of questions that you can always get in this type of questions in mole concept. Now the next part of it is simple one, oxidation state concept we will go with. Remember, I wanted to tell you hydrogen has +1 and -1, and -1 is always oxidation numbers. -1 is seen in metal hydrides like NaH, CaH2, LiAlH4. This is about hydrogen. Oxygen, all generally -2, +1 O2F2, +2 OF2. In hydrogen peroxide, it is -1. In potassium superoxide, it is -1/2. How many superoxides are known to you? KO2, RbO2, CSO2. These are the three most important superoxides known to you in chemistry. In these elements, the alkali metal will have +1 state. The remaining, in this case, oxygen will have -1/2. I also wanted to clarify some 2 or 3 very important peroxy containing compounds. H2O2, Na2O2, BaO2, H2SO5, H2S2O8 are some very important examples of peroxo compounds where oxygen is in -1 state. This is called Carros acid or peroxo monosulfuric acid. This is called peroxo disulfuric acid or Marshall's acid. This is about the oxygen's oxidation state. Next, if you see, if you are going with some very important aspects like certain compounds are there whose structures are not to be known. NH4NO3, NH4NO2, CaOCl2, CH3CH2OH. I am going into each one of them in detail. NH4 plus NO3 minus. X plus 4 is equal to 0. X plus 4 is equal to +1. X is equal to -3. Oxidation state of nitrogen in NH4 plus is -3. Here it is X. 6 oxygens -6 is equal to -1. X is equal to +5. Similarly, you calculate here, you get X is equal to -3, X is equal to +3. Suppose this is there, Ca2 plus will be there, Cl minus will be there, ClO minus will be there. Such a salt in chemistry is called mixed salt, where the oxidation state of chlorine is -1. Here it is +1 -2 is equal to -1. So chlorine will be in +1 state. So in bleaching powder, oxidation state of chlorine will be +1 and -1. Ethyl alcohol structure plays an important role. This is the structure of ethyl alcohol. You can see +1, +1, +1. Hence it will be -3, +1, +1, -2, +1, +1 and -1 get cancelled. Here it is -1. The oxidation states of carbon in ethyl alcohol will be -3 and -1. This is how you can actually calculate the oxidation state of carbon atom in different molecules. In the same molecule, one carbon has -3 state, other molecule has -1 state. You can calculate. Also, there are some other examples where you can also concentrate. That is, let us say, this is called tetrathionic acid. In this case, the oxidation state -2, -1, -1, -2, sorry. So -2, -1, -2. So it will be +5. Here also +5. This sulfur on both sides, sulfur 0. This sulfur both sides 0. This is one textbook example. Another example, Br3O8. So minus 2, minus 2, minus 2, plus 6, minus 2, minus 2, plus 4, and here plus 6. This is another important example of a molecule with different oxidation states. Suppose you are actually going with another example of a mixed oxide, Pb3O4. What will be the average oxidation state? Plus 8 by 3. But if you actually write it properly, it will be PbO2 dot 2 PbO. Here it will be equal to plus 4. Here it will be equal to plus 2. Therefore, plus 4 plus 2 plus 2 are the oxidation states of lead in a mixed oxide of lead called Pb3O4. So the average oxidation state is 8 by 3. After knowing the oxidation states, how to identify whether the reaction is a redox reaction or not a redox reaction. For example, if I take a combination reaction where H2 plus Cl2 gives 2HCl, 0, 0, plus 1, minus 1. This is a redox reaction where hydrogen is undergoing oxidation. Hydrogen is called as a reducing agent. Chlorine is called as an oxidizing agent. But another important example of a combination, NH3 plus HCl, NH4Cl, minus 3, plus 1, plus 1, minus 1, minus 3, plus 1, minus 1. You can see very clearly this is not a redox reaction. So every combination reaction need not be a redox reaction. Hint for you, in a combination reaction, if at least one of the reactant is an element, if at least one of the reactant is an element, then it is a redox reaction. Here both are elements. Here this is not an element, this is not an element, both are compounds, then it is not a redox reaction. For example, 2SO2 plus O2 gives 2SO3 is another example of a redox reaction where it is a redox reaction once again because one of the reactant is an element called O2. This is about combination. Exactly reverse to that of combination is decomposition. Here you can see once again decomposition reaction. I am taking two examples. Let us say this is one example. Another example is this. You can see very clearly plus 2, plus 4, minus 2, plus 2, minus 2, plus 4, minus 2. This is not a redox reaction. Once again the same technique you apply. During a decomposition reaction, if one of the product is an element, then only it is redox. If none of the products actually is an element, here both are compounds, it is not a redox reaction. Whereas you see here, this is plus 1, this is plus 5, this is minus 2, this is plus 1, this is minus 1, this is 0. This is a redox reaction. Thus, whenever you take a combination or a decomposition reaction, in a combination reaction, you can say that it is a redox reaction when at least one of the reactant is an element. In a decomposition reaction, you can call it as a redox reaction only when if at least one of the product is an element. Then after identifying this, you also should know the next part called displacement. Displacement reaction. What is this type of a displacement? Do you know this? Mg plus ZnSO4 gives MgSO4 plus Zn. Metal displacement reaction. Then what is this called? F2 plus 2KCl gives 2KF plus Cl2. This is a non-metal displacement reaction. Mg plus H2SO4 gives MgSO4 plus H2. These two come under the category of non-metal displacement. This comes under the category of metal displacement reactions. These are the various redox reactions that we come across. Now, one or two very important models of redox reactions are this. You check here, Cl2 in basic medium forms Cl minus, ClO minus when it is in cold and dilute conditions. Suppose the same chlorine in the same basic medium under hot and concentrated conditions gives Cl minus plus ClO3 minus. Suppose if there is a P4 which gives PH3 plus H2PO2 minus in basic medium. There is an S8 molecule in basic medium giving sulfide ion and thiosulfate ion. You can also take a nitrous acid giving HNO3 and NO. You can also take H3PO3 giving H3PO4 and PH3. Any number of examples you can take. This is MnO for manganate. Manganate giving permanganate and MnO2. These are some beautiful examples of disproportionation reactions. Disproportionation. You can see 0 here will become minus 1 and plus 1. 0 here will become minus 1 and plus 1. 0 here will become minus 3 plus 1. 0 here will become minus 2 plus 2. Plus 3 here will become plus 5 and plus 2. Plus 3 here will become plus 5 and minus 3. Plus 6 here will become plus 7 and plus 4. Redox reactions in which same element undergoes both oxidation and reduction simultaneously is called as a disproportionation reaction. I want you not to confuse with this. Suppose there is a permanganate ion giving manganate MnO2 O2. Here in permanganate this is plus 7. Here oxygen is minus 2. Here in manganate is it plus 6, it is plus 4, it is 0. Please make it a point, in this reaction permanganate is undergoing both oxidation and reduction, but this reaction cannot be considered to be a disproportionation reaction. No, no, no. Why? Because manganese is undergoing reduction, oxygen is undergoing oxidation. So it is a redox reaction but cannot be considered as a disproportionation reaction because one element manganese is undergoing reduction, other element oxygen is undergoing oxidation. Whereas in the other examples that you have taken, the element which is undergoing oxidation is the same one which undergoes reduction. So if the same element undergoes both oxidation and reduction, then only you should call it as a disproportionation reaction. This cannot be called as a disproportionation reaction. Another very popular example of disproportionation that you come across in D block elements is a cuprous ion in aqueous solution disproportionates to give cupric and copper. Exactly, if you see the reverse of it, comproportionation. If you say, let us say OF2 plus H2O gives HF plus O2. Permanganate plus Mn plus 2 gives MnO2. If you see, this is reverse. Here oxygen is plus 2, here oxygen is minus 2, and here oxygen is 0. This is exactly the reverse of disproportionation. Here manganese is plus 7, here manganese is plus 2, and both of them are getting converted to plus 4. One undergoes oxidation. This is called comproportionation. Did you understand the types of redox reactions that you have? All of you? Fine. Next, how to balance. While balancing reactions, only thing try to remember acidic medium. Wherever you want hydrogens, add required H plus ions, and before that for oxygen add required number of water molecules. Now if it is basic medium, same for oxygen, but for hydrogen add required number of H2O on side deficient and same number of OH minus ions on opposite side. Please see that these two rules are known to you. Whether it is acidic medium or basic medium, for balancing oxygen, add required number of water molecules wherever it is required. For hydrogen, if it is acidic medium, add required number of H plus ions. If it is a basic medium, add required number of water molecules on side deficient and same number of OH minus on the opposite side. So when you are balancing two equations, you will understand the concept better. I will do one acidic medium, I will do one basic medium. Permanganate, oxalate, H plus acidic medium, Mn plus 2 CO2. Now, reduction half reaction is permanganate reducing to Mn plus 2. Balance manganese, manganese is already balanced. Oxygen should be balanced. What is the rule that you should follow for oxygen? 4 water molecules must be added. Now oxygen is balanced. What about hydrogen? 4 2s are 8. So 8 H plus must be added. Mn plus 2 and 4 H2O. Then what about the next? Charges. What is the total charge here? Plus 7. What is the total charge here? Plus 2. Moreover, what is this? Reduction, gain of electrons. How many charge difference? 5 is the difference in the charge. So permanganate plus 8H plus 5 electrons gives Mn2 plus 4H2. This is how you balanced the reduction half reaction. Then coming to oxidation half reaction. C2O4 2 minus gives CO2. Then first carbon should be balanced. 2 carbons are there on the left side, 2 carbons on the right side. Luckily for us, oxygen already got balanced, only 2 electrons. This is balanced. Whether we are right or wrong, we can easily understand. Since it is reduction, gain of electrons, since it is oxidation, loss of electron, it is fine. To make the electrons equal, I multiply this with 2 and I multiply this with 5. Now you see, if anybody is asking, what is N factor of permanganate? Number of electrons lost or gained per mole of an oxidizing or reducing agent is called N factor, valence factor, valency factor. What is valency factor or N factor? It is the number of electrons lost or gained by an oxidizing agent or reducing agent in a redox reaction. For every 1 mole of permanganate, you have 5 moles of electrons gaining. So N factor of permanganate here is 5. Similarly, for every 1 mole of oxalate, 2 moles of electrons are lost. So N factor of oxalate in this reaction is 2. How many total number of electrons are participating in the stoichiometric equation? 5 2s are 10, 2 5s are 10. The total number of electrons participating in the reactions are 10. They may ask you questions here. How many H plus ions in the net equation? How many electrons in the net equation? The stoichiometric coefficients and so on. This is acidic medium. Let us say basic medium. Permanganate. Why should I take permanganate every time? I'll take Cl2 in basic medium, give Cl minus and ClO3 minus. I will actually balance this. Cl2 giving Cl minus, if you agree with me, should be reduction because 0 to -1. And then while balancing chlorine, so 2Cl minus. Luckily, no oxygens, no hydrogens, only electrons, so 2 electrons. If anybody is asking what is N factor of chlorine in this reaction, only when it is acting like a, this is a reduction. Oxidizing agent, you should say the answer as 2. But the question is very much important to be understood. Oxidation half reaction. Cl2 gives ClO3 minus. First balance chlorine, 2ClO3 minus. How to balance oxygen? 6 oxygens are there. So I am adding 6 water molecules. 6, 2, 3 are 6. 6 water molecules I am adding here. Then hydrogen. How many hydrogens are there here? 12. None here. So 12 water molecules on the side deficient. 12 OH minus on the opposite. Please make it a point. This is the important step. 2, 3 are 6. 6 oxygen, 6 water. Now hydrogen, 6, 2 are 12. 12 hydrogens on the left side. To make it equal, on the side deficient 12 water molecules, same number of OH minus. Now if you are interested, you can cancel this. You can cancel this and put 6H2O. Total number of charges here, 12. Total number of charges here, -2. Difference is 10. So I am going to write Cl2 plus 12 OH minus gives 2ClO3 minus 6H2O plus 10 electrons. If anybody is asking you what is N factor of chlorine acting like a oxidizing agent, say 2. What is N factor of chlorine acting like a reducing agent, say 10. How many electrons are participating here and multiply with 5. If you see how many moles of chlorine are there here, 5. How many moles of chlorine are there, 1. So 6 chlorine total. How many moles of chlorine are participating in the reaction? 6. 5 here, 6. For 6 chlorines, how many electrons are participating? 10 electrons. 5 2s are 10 and then 10. So for 1 mole of chlorine, how much is required is 10 by 6, which is equal to nothing but equal to 5 by 3, which is the N factor of chlorine in the net reaction is 5 by 3. How did I do? Only as a oxidizing agent for every 1 mole 2 electrons. Only as a reducing agent for every 1 mole 10 electrons. Total number of electrons participating are 10. For these 10 moles of electrons participating, how many moles of chlorine are involved? 5 here, 1 here. 6 moles of chlorine involve 10 electrons. 1 mole of chlorine involve how many? 10 by 6, which will be equal to 5 by 3. N factor of chlorine in this reaction is 5 by 3. This is another important aspect. Last part of stoichiometry, if you go with chemical equations and calculations. Edit cheddam ikkada. Now the last part of stoichiometry that we wanted to discuss is chemical equations and calculations. So chemical equations and calculations. As you know very well, every chemical reaction is balanced with respect to mass. This is law of conservation of mass, and such an equation which is a balanced equation, let us say CH2 gives NH3. Suppose if you have this is a skeleton equation, skeletal. Now if I put this and put this is a balanced stoichiometric equation. For such a equation, how to do the calculations and how to proceed with the questions that are there, when how much reactant has reacted, how much product has formed, what is the yield of the product, is there any purity, is there an impurity, all these things can be calculated. Is what is the next question. Suppose you are actually going with a simple question, C plus O2 gives CO2. You can very clearly see, you can hear also both of them, 28 grams, 3 into 2 grams, 2 into 17 grams. Here also 12 grams, 32 grams, 44 grams. These are all weights, but how to proceed? Here, suppose moles, 1 mole, 3 moles, 2 moles. 1 gram atom or 1 mole, 1 mole, 1 mole. How to actually proceed with what type of questions can you get here? Suppose they say C plus O2 gives CO2 is called combustion. Combustion of carbon produces carbon dioxide. Now suppose you are having a question, 3 grams of carbon produces dash liters of CO2 at STP. Simple question, 12 grams will produce 22.4 liters. 3 grams will produce how much? Happily you can say 5.6 liters. This is question number 1. Easy question. Second, now comes a very important question. 3 grams of carbon reacts with 10 grams of oxygen to produce dash grams of CO2. A very important type of a question. This question is the first one where you can identify what is the excess reagent, what is the limiting reagent. Now, carbon, oxygen, carbon dioxide, 3 grams, 32 grams, 12 grams, 44 grams. Now, I am actually going into rough work and find out limiting and excess reagent. Carbon, oxygen. The question has 3 grams of carbon, 10 grams of oxygen. Wantedly, I am selecting a wrong path to understand the question in a better way. You know very well, 12 grams of this require 32 grams. Suppose if I am taking all the 10 grams of oxygen that I have taken completely reacts. 10 grams require how much? So W carbon is equal to 12 into 10 by 32. 12 into 10 by 32, 120 by 32 is 8 ones are, 8 fives are, 8 4, 14, 3s are, 75 grams. So for this 10 grams of oxygen to react, how much carbon is required, Andy? You require 3.75 grams. But do you have 3.75 grams? No, you have only 3 grams. So this is not the correct path that we should follow. The other way around. See, CO2, 12 grams, 32. So previously I started with the 10 grams. For this 10 grams of oxygen to completely react, we require 3.75 grams, which is not there with us. So we stopped there. So this is not correct. So now let us go with, this is 3 grams. How much do you require? W oxygen required is 3 into 32 by 12, which is 8 grams. Means for the 3 grams of carbon that you have taken, how many grams of oxygen is sufficient enough? 8 grams. But how much we took? 10. Yes. We require 8 only, but we have 10. This is the correct path. Now, 3 grams require 8 grams, but we have 10 grams. So, how many grams excess? 2 grams is excess. Did you understand how to identify limiting and excess reagent? Now tell me, in this case, the reagent which will completely, or the reactant which will completely react is actually carbon. It is called limiting reagent. Oxygen is actually taken in excess. It is called excess reagent. How much excess also? I actually calculated 2 grams. Now, while actually calculating the amount of the product formed, who will decide the amount of the product formed? The amount of the product formed does not depend on the amount left over. It always depends on amount reacted. So, we better select the reagent which is limiting. So, we will ignore oxygen. 12 grams required gives 44. 3 grams gives how much? So, happily your answer will be 11 grams. So, 3 grams of carbon when reacts with 10 grams of oxygen will produce only 11 grams of carbon dioxide. And therefore, if a question is, what is the limiting reagent? Answer is carbon. What is the excess reagent? The answer is oxygen. How much is the carbon dioxide formed? It is 11 grams. How much is the oxygen left over? 2 grams. If they ask, what is the weight of the gaseous species left over after the reaction, the answer should be 13, because 11 grams of carbon dioxide formed and 2 grams of oxygen left over, both are gaseous in nature. So the total weight of gases left over after the reaction is 13 grams. A very, 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 very important model of a problem. Another one. Suppose another one, N2 plus O2 gives 2NO, all are gases. Suppose if they say I took let us say 2 liters of it and I took 3 liters of it, how much is this? So once again, it is your primary duty to actually go to identify limiting and excess reagent. So I go with, I select a better one which is a tougher one. Let us say I actually will do one thing, 5A plus 3B gives 2C. I took 2 moles of this. I took 2 moles of this. Tell me the story of it, they say. Now, I wanted to go with A and B. 5 will react with 3. 2 will react with how much? Suppose I take this. 2 will react. 5 requires 3. 2 requires how much? So, number of moles of A will be 10 by 3, 3.33. So, we require 3.33 moles of A. For 2 moles of B to react, we require 3.33. We don't have. This is not a correct way. A, B, 5, 3, 5, 3. Suppose you take 2 moles of A, then how much B? NB will be equal to 6 by 5, 1.2. Yeah, for 2 moles of A to react, we require only 1.2 and we have 2 moles of it. Yes, this is the correct way. So 5A, 3B, 2C. 2 will react with 1.2, but we have 2 moles, so 0.8 moles excess. Limiting excess, limiting. Who will decide the amount of C formed? Limiting. Who is that? A. So 5 will give 2. 2 will give how much? 2 into 2 by 5, which is equal to 0.8. Number of moles of C is equal to 0.8. 5 moles of A will give 2 moles of C. 2 moles of A will give how much? 2 into 2 by 4. 2 into 2 by 5, which is equal to 4 by 5, 0.8. The limiting reagent is A. The excess reagent is B. And the amount of C formed will be 0.8. Purity problem. 10 grams of CaCO3 liberated 1.68 liters of CO2 at STP. Percentage purity of CaCO3 is dash. CaCO3 gives CaO plus CO2. 100 grams will give 22.4. 10 grams must give 2.24 liters. So, if the purity of this 10 grams is 100%, how much carbon dioxide you should get? 2.24. But how much did you get? Only 1.68. So, if it is 100% pure, you get 2.24. Therefore, percentage purity is equal to 1.68 by 2.24 into 100, which is 75%. This is a purity problem. One more such question. Did you understand, all of you? 100 grams will give 22.4. 10 grams should give how much? 2.24. If it is 100% pure, you will get 2.24 liters of carbon dioxide. But how much did you get? 1.68 liters only you got. So therefore, the purity is only 75%. Same question. What volume of CO2 is liberated when 20 grams of 10% pure CaCO3 decomposes? How many grams? 20 grams. How much purity? 10%. CaCO3 gives CaO plus CO2. 100 grams will give 22.4 liters. 20 grams must give how much? It will be 1/5 of it. 1/5 will be 4.48 liters. But the purity is only 10%. So VCO2 will be 4.48 into 10 by 100, which will be 0.448 liters only will be obtained. Since the purity is only 10%, you get only 0.448 liters or 448 ml. Suppose dash grams of 20% pure CaCO3 produces 2.24 liters of CO2 at STP. CaCO3 once again CaO plus CO2. 100 grams 22.4. 2.24 will be how many? 10 grams. If you want to produce 2.24 liters, you require 10 grams. So for this 10 grams, this is when it is 100% pure. But you are telling the purity is only 20%. You want 10 grams of CaCO3 to produce 2.24 liters, but the purity, when will this 10 grams give 2.24 when it is 100% pure? But the purity is only 20%. So will it give 2.24? No, because its purity is less. The purity is less, carbon dioxide liberated is less. We want 2.24 liters of carbon dioxide, but I am giving you a less pure substance. So therefore, do I require more than 10 grams or less than 10 grams? More than 10 grams. So this is now WCaCO3, which is 20% pure, required is equal to 10 into 100 by 20, which is equal to 50 grams is your answer. One last point I wanted to clarify. Whenever you are writing combustion reactions, in this case, while solving it, when they don't say anything, you should always consider water always to be a liquid while solving the question. It should not be considered as a gas, because if nothing is mentioned, the reaction is carried out at room temperature. At room temperature, water is a liquid. So if they mention any high temperature above 100 degrees, then only. So while solving these questions, it is also an important aspect. Thank you. Thank you so much.